Welcome back to the second session of Basic Mathematical Intuition for Robotics. Thank you all for attending the first session and showing so much of interest and all of the questions that were asked after the course and all of that. Also, for all of those who are joining back for the second session, thank you again. Hopefully, these sessions are able to give you guys a little bit more clarity towards the type of mathematics that go in for coding the robots when you guys actually plan of creating robots, whether it's for competitions, hobbies, or just projects that you're doing as a hobby. Our last session, we have the entire video put up on both the IEEE RAS PSU Robotics YouTube channel as well as the PhysiFacts YouTube channel. And from this session on, we will be live streaming on the PhysiFacts channel itself. For the initial first course, it will happen on PhysiFacts, whereas our second course, which is Practical Mathematics for Robotic Applications, that course will happen on the IEEE RAS PSU Robotics YouTube page. Right now, we have 28 people on the live stream. It's still increasing, so there are quite a few people joining in. So I think we'll wait for a few more minutes before directly getting into the session. In this session, we will be talking about the overall transformation matrix, and we're also going to be talking about what exactly kinematics is, which in fact is the basis for robotics and all of the mathematical things required for robotics. Before we start off this session, we would have to go through a recap of everything that was done in the last session. And with the number of people that have joined in now, I guess we will start. Do remember that, yeah, I am looking at the live chats. So if you do have any questions, please do comment them as and when you get the questions. I might not be addressing them directly while the course is going on, but we will try to finish the course within 50 minutes and have 10 minutes right at the end, which are dedicated to answering all of your questions and all of your doubts, whether it's related to this specific session or towards the course or the IEEE RAS chapter or PhysiFacts. We would love to answer all of your questions, so please do remember to keep doing that. Okay. Also, there is a latency time of around 20 seconds between when I actually give out the session and it reaches all of you live. So between the chats and me answering the chats, there would be around 20 seconds of delay. So be prepared for that. So just to go to a recap of whatever happened in the last session, we started off the class by explaining how robots are to be classified when it comes to mathematical robotics. When we're modeling it mathematically, we have to define a robot, we have to classify it based on the number of joints and the type of joints. And we said that there are two major types of joints. One is a revolute joint, which can rotate about one specific axis only, and the other is a prismatic joint, which would move along a single axis. With these two types of joints, we started categorizing different types of robots. The first type that we spoke about were planar robots, which had two joints. We also spoke about why two joints would be necessary for this robot to work, mainly because if we had only one joint, we would be able to move around a circle and not reach an entire plane. or in case of a prismatic joint, if we had only one prismatic joint, we would move along a line only. Similarly, we then went on to saying that planar robots can move only on a plane and cannot reach any form of height. So we went to three-dimensional robots, starting off with the Cartesian robot, which had three prismatic joints, which could move along all three principal axes, which could potentially allow this robot to reach every single position in its workspace. Now, the workspace was the area in three-dimensional space where this robot's end effector, which is the last point on which the tool that it's being used, whether it's a drilling tool or a gripper for a pick and place robot or spray paint, etc., etc. Sorry for the disturbance. I think there was a slight error in the slight issue with the internet connectivity. Yeah, so if by chance any of you cannot hear what I'm saying or there's any problem with the connection, please do mention it in the chat as soon as you can so that we can rectify it as soon as possible. So our Cartesian robot, as we said, can go in three dimensions in a cuboidal workspace. And it has three prismatic joints. Similarly, our spherical robot has two revolute joints and one prismatic joint, which corresponds to something similar to our spherical coordinate system, where we had one joint for the value of theta, then we had another joint for the value of phi, and finally we had one joint for the value of r. And this particular robot would be able to reach any space in three dimensions, and the workspace would be a sphere. It would have a spherical workspace. Similarly, we have our cylindrical robot. Our cylindrical robot has three joints again, and one is a spherical joint, is a revolute joint, one revolute joint, and two prismatic joints. So this again would be able to move in three-dimensional space and would have a workspace which would be a cylinder. So it would have a cylindrical workspace. Then we came to how we could add even more joints to a robot to create almost any kind of robot. And so we would rename the robots in a more generalized way, which could be 1R, 1R, 2P, which would mean that there's one revolute joint and two prismatic joints, like the cylindrical robot, or it could be 3R, 5P, which would mean there's three revolute joints and five prismatic joints, and so on and so forth. So this particular robot here would be 1R, 1R, 2R, 3R, and 1P. So that would mean 3R, 1P robot. After all of this, we came to our actual mathematical concepts, which began with the concept of frames. So our frames, we had a few things that we could do with the frames. The first one was translation of a frame, and we would have to find out where the new point is with respect to the new frame. So in case we had a point here, we could move the frame parallel to the previous frame to find a new frame, and we could try to figure out what is the location of this point with respect to this new frame when we know what it is with respect to the old frame. To figure this out, the one thing that we need to know is what is the location of the origin of the old original frame with respect to the new frame. If we know that, according to our formula, we simply would have to add that location, the origin of frame A with respect to frame B, to the point P with respect to A, to find out what is the value of that point with respect to the new frame, which is B. The other thing that we could have done is rotation of a frame. Rotation of a frame could be about x-axis, y-axis, or the z-axis through an angle of alpha, beta, gamma. And we saw that we'd have to multiply this particular point with this rotational matrix, which is given over here. If the rotation is about x-axis, you would have to multiply this matrix with the point, which is represented as a column matrix. All points for robotics is represented as a column matrix. So we would have to multiply that column matrix, which would be a 3 cross 1 matrix, one for x, y, and z, and we would multiply that with this rotation matrix. And in the rotation matrix, we would substitute theta as the angle by which the rotation has occurred. Now that could have been x or y or z accordingly. But we also saw that it's not necessary that it would be a rotation solely on one axis like this. This is a rotation about the x-axis. We saw that it could have been a rotation based on all of the axes, like this. In that case, what we did was we had to define whether it's rotating about the moving frames or whether it's rotating about stationary frames. So if it is rotating about moving frames, which means it rotates about its y-axis, the new y-axis after rotating about x. If the order in which it's being rotated is x, then y, then z axes, we would have to use this particular formula. So this is very intuitive, which is obviously from this formula we know that if there's a rotation about x, we would get a new frame and we'd multiply that with the point to find out what the new point is with respect to this new frame, which is rotated only about x. Now, once we rotated about y after that, we'd simply be doing this multiplied by that new point, and we keep doing that till we get what the point is when after rotation about each of the frames. But that wasn't the only way of doing it. We could have had it about the fixed frames, where the fixed frame is when it's rotating about the original global axes. So a rotation about fixed frame would be like this. The y-axis, instead of rotating about this, we would be rotating like this about the original y-axis. So what actually happens is we're trying to figure out what happens when both the things happen, an overall transformation. To figure out an overall transformation, we'd first have, if suppose the transformation was as such, it was first moved about the x-axis by, let's say, 10 units, then it was moved about the y-axis the local y-axis, so the y-axis by 15 units, and then it was moved about the z-axis by 20 units, and then it was rotated about the x-axis by 30, about the y-axis by 45, and then about the z-axis by 60 degrees, we'd have to find out where this new point is with respect to that. So to do that, we do it in a slightly different way. Instead of translating this first, what we do is we do all of the rotations first. So to do the rotations, you would see we could do rx 30 degrees, ry 45 degrees, and then rz 60 degrees. You'd see that we now aligned our frame parallel to the new frame. We can find out what this point is with respect to this using the formula that we got right here. And after getting this, once we have this now, we can see that our origin has not moved. And because our origin has not moved, we know where the origin of the original base frame was with respect to this. We also know where the origin is with respect to this, because the origin hasn't moved. So we would simply translate by that much, which would be movement about the x by 10 units, then movement about the y by 15 units, and then movement about the z by 20 units. And we'd reach the exact new point, and we could find out what this point is. So we'd actually see that the new overall transformation would be a rotation about x, y, z. Here we're talking about rotation r, x, y, z, x and y and z, as a multiplication. This entire thing we're going to calculate to find a new rotation matrix, a single 3 cross 3 matrix by multiplication, and we're going to call that as r, x, y, z, and that into the original point plus the origin, and we'd get it. But this has its own disadvantages that we're trying to remove. So if we actually expand this and do a little bit of mathematics that we will not be going into in this course, we can rewrite it as a single transformation matrix. Obviously, we have to figure out what this transformation matrix is, so that we don't have to have this addition and we have just a single multiplication with a transformation matrix that takes care of both rotation as well as translation. And that matrix is actually like this. It's a 4 cross 4 matrix where we have this BPA origin, the origin of frame A with respect to frame B, the x coordinate, y coordinate, and the z coordinate in the last column, and this R11, R12, R13. This particular thing is actually a 3 cross 3 rotational matrix, which is this specific rotational matrix. So this rotational matrix comes in here, and we have to add in a few what's called as dummy numbers, which it has to be 0, 0, 0, and 1 to keep all of the properties of this the same. So since this is now a 4 cross 4 matrix, we can't just multiply it with AP. So we have to add a dummy number to the AP as well. So that goes on to be like this. We find out that the new point with respect to the old frame is actually is this transformation matrix into the coordinates with respect to the original frame with the dummy variable 1, and we also get a dummy number 1 here and a dummy number 1 over here as well. So why this is such a useful thing is because of two reasons. The first one is, okay, this is from frame A to frame B, but what if you had multiple frames that you had to go through? What if you had one frame over here which was rotated like this, and then the next frame was over here rotated like this, and you had to find out what is the relation from this frame to this frame, but you only know the relation of this frame to this frame and this frame to this frame. So to figure that out, again, not too hard, once we have it in that form, all we have to do is multiply each of the transformation matrices. So in this case, I took an example of 6 different frames, and I want to find out what is the relation between the 6th frame and the first frame. The actual answer is just the multiplication of the relation between the 6th frame to the 5th frame, the 5th frame to the 4th, 4th to the 3rd, 3rd to the 2nd, and finally the 2nd to the 1st. If you just multiply them, you get the overall transformation matrix, which would relate the 6th frame with the 1st frame, which is actually really cool. The second use of this transformation matrix is, suppose we know what the relation is to go from this frame to this frame. If we know it with this frame, multiply by the transformation matrix, we find out what this point is with respect to this frame. But what if we know what the point is with respect to this frame, and we want to find out what is the point with respect to this original frame? We only know how to go the other way around. By converting that transformation matrix to just one matrix, one 4x4 matrix, we can find out the inverse of a matrix just like this. So if we know what B to A is, the transformation from A to B is actually just the inverse of that matrix. And inverse of a matrix, we all know you have to take the adjoint matrix, and we'd have to divide it by the determinant and do all of that to find the inverse. But the point is that we are able to just get an inverse and find out what the opposite relation is. There are slightly more details to cover in this particular topic, the inverse of a transformation, such as singularity cases and things like that. All of that will be taken in detail along with questions and problems in the next course, which will be on the IEEE RAS PS University Robotics channel in the following week, the practical mathematics for robotic applications. So the next concept now is, okay, we have this transformation matrix that has a rotational part and a final part. What do we do with these? There comes in the DH parameters. So the DH parameters is a method by which we go about forward kinematics. What is forward kinematics is what we should first be answering. So forward kinematics is, simply put, if we know what these joint values are. Suppose we say that this is a revolute joint. So let's say this is rotated by 30 degrees. Let's just say 30 degrees. This, being a prismatic joint, is at a length of, let's say, 2 units. This, being another prismatic joint, is at a length of, again, 2 units from this joint. What is the location of this end effector, the tool? So we know what these angles are, but we have to find out what the position of this end effector is. Now this could be done using geometry. People who are good at geometry would already be telling me that, okay, you could find out that this is 30 degrees, so we know that we can continue further calculations of this 30 degrees, calculate this distance, which we said was 2 units or something like that, and we could continue adding in all of that to figure out what this is. But the problem is, this machine has only 3 joints. A normal machine would have so many more joints than that, and if we were to geometrically calculate it every time, our microcontroller that's actually doing all of the processing on the robot would not be able to calculate it in a sufficient amount of time. We would require more time to do these calculations, and nobody wants a slow robot. So to create a relation between this base frame and the final frame, we use something called the DH parameters. So what these DH parameters are is by calculating them, you can directly apply them in a formula to figure out the relation between this frame and the final frame. And we can simply be putting in these different joint values, these joint variables, like the heights, the distances, and all of those, the link lengths, the angles of rotations, and all of that. And we could, in principle, find out, not only in principle, we could practically find out what the relation is between this frame and the end effector. So that is the DH parameters, which is very, very, very important when it comes to actually modeling your robots. If you were to use any robot modeling software where we actually model them, they generally use the DH parameter. So you'd have to fill in this particular table and you'd have to supply in all the variables, and we'd get the outputs accordingly. So what this table actually is, before we start filling up this table, we have to assign frames. So that is actually step one to creating the DH parameters. So we would have to have one frame for one base frame and one frame for every single joint. So if you see, this is a joint, so we have a frame attached to it. This is the end effector, so we have a frame over here, and this is the main final frame that we want to reach. This is a joint, so we have a frame here, and we have finally one frame here at this joint. So why these frames are in these specific orientations, as you can see, I've kept the z-axis up here, the z-axis is up here, the z-axis up here, but there's a twist. Here the y-axes are pointing in this direction, but for this frame we had to make the y-axis point front, and in this frame we actually made the y-axis point down. So why all of those happen is because of it becomes easier, and in fact it becomes possible to assign these values to this table only if they are aligned like that. Now there are methods of aligning those frames, the way you select how the frames should be. Again, that will be taken in detail in the next course. This course is most about intuition, so that you know what has to be done. How exactly we go about that is saved for the next course, for those who actually want more mathematics. So a rotation about the x, the first thing that we have to do is figure out to move your frame. This is the frame number. So to move your frame number from frame 0 to frame 1, how much would we have to rotate about the x, then translate about the x, then translate along z, and then rotate about z. That's exactly what we're doing in that order. We're going to first take our frame and see what values do we have to rotate, translate, and rotate about the x and the z axes. For example, this one, if this was rotated at some degrees, obviously from the base we'd have to do some rotation, but we're not going to get into that right now. But we'd see the first step was rotation about the x-axis. So we'd see that to go to the next frame, we don't need to rotate about the x-axis. The second step was translation about the x-axis. Yes, we'd have to translate it by some value. Let's say maybe this is 2 units. So we'd fill in a 2 right here. Then we'd have to see translation about the z-axis. And no, we don't have to have any translation about the z-axis. And then rotation about z-axis is also not necessary. In fact, to go, this would be frame 0 and this would be frame 1. And to go from frame 0 to frame 1, we might have to have a rotation about the z-axis. Because if this was rotated about the z-axis, we'd have some form, some angle by which this base frame would have had to be rotated to match this frame. This now that we're showing is rotation from frame 1 to frame 2. Then to go from frame 2 to frame 3, we'd not we wouldn't actually have to have a rotation about x, we wouldn't have to have a translation about x, but we would have to have a movement about x, about z. So a translation about the z-axis would be needed. And as you can see, just a translation would still not do it. We would also require a rotation by 90 degrees, and that would make it match. Now note that this particular distance that we traveled, this distance would be a variable. So from 1 to 2, this right here would actually be a variable. It would not be a constant because that's a joint. So that is what our joint variable is. We put in our joint variable over here, and the rotation about z would be a constant in this case. It would be 90 degrees, as we just said. But when it was going from the base frame to the first frame, this would have been a variable, because we just saw that while going from the base frame to this frame, it could literally be anything. It could be 30, 45, 60, 90, anything. So it would be a variable. After we finished aligning that to this, we'd go from frame, it was base 0 to 1, 1 to 2, 2 to 3, 3 to 4 would actually require a rotation about the x-axis initially. It wouldn't require any translation, but it would require a rotation about the x-axis. So that would be minus 90 degrees requirement. And then it would require a translation by some amount, which would again be a variable, because this by itself is a variable. Anyway, once you fill in this table, for each frame, you can make a transformation matrix. So this, by substituting in your values of alpha, theta, d, you could actually create a transformation matrix that goes from frame 0 to frame 1, 1 to 2, just by substituting the values that you had put in over here, alpha, a, d, and theta. By putting in those values over here, you would get a transformation matrix. And then, simply by using this particular property, where you multiply each of the transformation matrices, you would get a final transformation matrix that relates the first, your base frame, to the final frame. And of course, there are alternatives to the DH parameters. As I said, there are geometrical means. There are other things like screw theory representations and Hayati-Roberts representations. But all of those methods have their own pros and cons. And the DH parameters is the most widely used. So even though this looks like a lot of things that you have to do, you first have to create this table over here. Once you fill up this table, you have to find out the transformation matrix for each particular frame, and then you have to multiply all of them to get the final transformation. The truth is, because you're using DH parameters, there are a lot of inbuilt functions in most libraries. You get libraries that take care of all of these DH parameters, your transformation matrix calculations, just as you provide them this particular table. So once you give them that table, it does the rest of the work for you. So it's not that much of a deal, and that's why we generally go with DH transformations. Now, the thing is, we started off to figure out what is kinematics. So kinematics, as we said, is we know this frame, we know all of the angles. What is the location of this final end effector? We have to find out where is the final end effector when we know the values of all of these variables. The cool thing is, now that we have this particular, using these matrices, remember that a few of these thetas are constant, but a few of them are variables. And from this particular thing, you'd see that in each row, we'd have one variable, right? So from 0 to 1, theta was actually a variable. From 1 to 2, we had di as a variable. So we'd have one variable in each of these transformation matrices. So since there are 1, 2, 3 joints, we'd actually have 3 variables. And those 3 variables would be put into this particular matrix and multiplied from here to get a final transformation matrix like this. This is a final transformation matrix. We'd get a final transformation matrix of this form. And this particular final transformation matrix is relating our base frame with our end effectors frame. And we know that for this transformation matrix, we have all of our origins. We have this to be our origin of our frame with respect to the new frame, our original frame with respect to the new frame. So that directly means that these 3 points, the last column of our final transformation matrix that we got after multiplying all of the transformation matrices, after finding out all of these, is going to give us the location of our end effector, because the end effector location is at the origin of the final frame. And we know that the origin of the final frame is at this specific place, because these 3 represent the origin with respect to the old frame. So once we know what this is, we can actually go ahead and figure out, just with this one transformation matrix that we get, we can actually figure out that if we were to have this angle as 30 degrees, this length as some length, this length also at some length, we could find out exactly where this final position is with respect to the base. And that is called forward kinematics. And that's obviously very, very necessary for any robot to know. When you are a robot, you can't figure out much of where your final end effector is. What you can find out though is what are your joint variables. As a robot, we know what angles your servo motors are outputting, and just by knowing what angles your servo motors are giving as an output, we can find out what these angles, what the joint variables are, and what the joint links are. Once we know what all of these joint lengths and all of those things are, we can find out what the final frame is. I know I'm repeating this multiple times, but it is very necessary to stress on understanding the concept and the difference between forward kinematics and inverse kinematics and why we're using them. Because yet again, we might have a lot of people trying to figure out what the difference is, like why in the world we're doing this. Hopefully this is making a lot of sense to you guys as to why this is happening. Similarly, we have to go in to now find out what inverse kinematics are. So we found out forward kinematics is given joint variables, we have to find out what the location of the end effector is. Where is the end effector? For most applications, for most robotic applications, using computer vision and things like that, we would know where our final position is. But our aim is to find out what angles need to be given to reach that end position. For example, here, if we were to reach this minus 3, 2, 2, we know that our end effector has to reach minus 3, 2, 2. But we need to find out What are the joint variables? How much does this have to move? How much does this have to move? By how this be turned? Probably this much. This would have to maybe move up a little bit more. No, it won't have to move up. But yeah, we'd have to do all of this to just figure out how we could make this point reach this point. What are those angles? And that we do by inverse kinematics. That is inverse kinematics. When we know our end effector location, we have to find out the required joint variables. And that is done again using this same transformation matrix that we found by multiplying all of these transformation matrices in this fashion to get a final transformation matrix which is in this fashion. We know now that these values, which would be in terms of variables, these values and these values would have all of those variables given, should be a specific number. Generally, these would give us the orientation of our end effector. So for example, if we look at the robot that we built the other day, this end effector, right now we do not have a link. But if we were to go all the way over here and rotate it down, it's lucky that we are getting this, and that happens because we haven't really had we don't have freedom to rotate this particular thing. But if we did have that freedom to rotate it about this axis, maybe we'd require the end effector to be rotated like this. Maybe we'd want the end effector to grip onto this in this particular fashion, etc., etc. So this would add in actually another joint and another variable to our original matrix that we had, and all of those rotations, the variables would fall inside this rotational area, and our prismatic movement, our location, our main location would land in these three places. Now just by knowing what the location is, 3, 2, 5, let's say, we would have to equate this to that and find out what the values of the variables should be, and we would output those values to our microcontroller, and it would immediately move to that position. And that is inverse kinematics, and that is what generally is on the microcontroller present in our robots. Now the thing is, we went through what forward kinematics is and what inverse kinematics is. The thing is, even though we know all of these, there's still a lot of problems that start coming in, which is what our next session will be about. And that session brings in what happens to when you have an object in between. You have to avoid it. Again, most people when in a competition would say, okay, we have a computer vision, we have a camera, we're going to see the object, and we say don't hit object. But that's not really how coding works. The computer needs to know exactly how it would have to move its joints to avoid those objects, and there's a lot of other problems that come in and a lot of other considerations that have to be made while designing a robot, and that is what the next few classes are about. Now, inverse kinematics, now though you have a basic idea of what inverse kinematics is and how it's done, we still haven't really solved a single problem, and there are things that there are problems that you'd run into if you were to actually solve this problem or try to code it into a microcontroller for a robot. Now the thing is, we will not be covering that in this course with that much of detail, which is why, again, I'm stressing that for those of you who are interested in that type of mathematical actual application and actually doing the math, we have a second course coming up which will be hosted on the IEEE RASPES University channel with a few other teachers who will be teaching you how all of these are actually applied. But with that, we do come to the end of the explanation for this particular session, and we are open to any questions that any of you have with regard to this session or anything else. So, do any of you have any questions? Do comment on the chat section and I will respond to all of your questions and try answering them as best as possible for the next 10 minutes. A lot of you were asking for a Blender course in the last session. So because all of you were asking for the Blender course and we got a few requests after the session as well, we have decided that we might have a Blender session after the robotics course too. So that would probably, if it happens, it would happen maybe in June. And if you all are interested, we could have that as a series as well and not just a single session. So apart from that, I still don't see any questions coming up on the live chat. So if you guys have any questions, whatever it could be, you could mention. If you don't have any questions, please do give in feedback so that we can make the sessions better. I know today there was a slight hiccup for a few minutes due to some connectivity issue. Hopefully that didn't bother it too much. If anyone has any feedback, whether it's bad or good, please do let us know. Any suggestions, anything, if you don't have any questions. All of these sessions will be available both on the IEEE RAS page as well as the PhysiFacts page. So anyone who's interested in watching these later on or recommending anyone else to watch them, they can watch them later on as well. But again, we do suggest that you watch it while it's live so that questions can be answered then and there itself. And live sessions are in general proven to be better for students to understand because you can go back and rewatch it and watch it at your pace later on. The next session onwards, which is session 3, 4, 5, 6, 3, 4, and 5, they would be slightly shorter. They won't be 1 hour long. The entire content will get over within 35 minutes and we'll spend 10 minutes for questions and answers, which would make them 45 minutes for the entire session. So we have one question from Vaishnav Bala saying, like how we have rotation along moving frames and fixed frames, do we also have translation along fixed and moving frames? Yes, we do have translation along fixed and moving frames, and it goes in the exact same way we did for rotation about fixed and moving frames. So in case of rotations about fixed and moving frames, we saw that if it was a moving frame, we went as pre-multiplication to find out the overall rotational matrix. So we multiply the final point with respect to this overall rotational matrix. And this overall rotational matrix, to find it, if it is a moving frame, we always go in the reverse order. It's called pre-multiplication. So it would be Rx pre-multiplied by Ry pre-multiplied by Rz. Similarly, if we were about the fixed frame, we do post multiplication to find out this overall rotation matrix, which would be Rx multiplied by Ry multiplied by Rz in a post multiplication. Post meaning we multiply to the right. Similarly, if we were having translations, if the translations were about the moving frames, to find out the overall translation, which we said over here was simply multiplication, yes, your question is very much valid. If it was translation about moving frame, a transformation about moving frame, if it was a transformation, then we would have pre-multiplications to figure out. So we do the first transformation matrix, pre-multiplied by the second transformation matrix, pre-multiplied by the third transformation matrix to find the overall transformation matrix and multiply that by the point. If the transformations were about the fixed frames, we'd have post-multiplications for each of the frames. In case of translation is just the if it's not a transformation, that means it's not both translation plus rotation, and it's just translation, it's just movement. That really doesn't depend on the order, because no matter which order we go to, if we start off at the origin and we move by 3 units in the x direction, 4 units in the y direction, and 5 units in the z direction, you would reach 3, 4, 5, which is the point, and your origin of the old frame with respect to the new frame would be corresponding to that point. Whether you go x, y, and z, or you go z 5 units, then y 4 units, then x 3 units, you'd still reach at 3, 4, 5 itself. So if it's just translation, your frame, the order does not really matter. But if it is a transformation, yes, it does matter, and you do have pre-multiplication and post-multiplication. Are there any other questions? Any other questions, any other feedback, anything? There's 3 more minutes and then we will be ending the live session for today. Tomorrow's live session will start at 4:30 again, Indian Standard Time, and it will be a slightly shorter session for about 45 minutes. If there's anyone who has absolutely no doubts whatsoever, can they please comment saying we have no doubts? I would really like to see how many people have no doubts. So the next series, it's going to be about practical applications of all of these. So here I just spoke about the way you find the DH parameters and how you're going to apply them. But I haven't actually shown any application of these DH parameters. We haven't actually done a problem. So we haven't taken a real life robot example and shown how the math is done. So the next course, the next series will be about going into slightly more detail. We will talk about things called singularities, the problems that you'll be facing while determining all of these things. And we'll be talking about how exactly you assign the frames for DH parameters. We'd actually do a problem so that you understand the actual application. And hopefully after that session, that entire series, you would be able to code for your robot by yourself. Right now, if you actually do try to take out a robot and start coding, you would come across hiccups, and you would be like, okay, there are certain other issues that are showing up. So hopefully we will fix all of that in the next course. Marcelo Acevedo says the session was good. Thank you so much. I really appreciate it. So the time is up, and